Hello. Thanks everyone for coming today. My name is Simon Holman. I'm working with Netronome on primarily open source upstream facing activities. Today I'll be talking about two of those activities, and the first one is in this presentation, which is about Open-NFP. So I'll start by talking a little bit about what Open-NFP is, and then briefly cover two models that can be used to offload it in conjunction with the kernel. And then I'll do a little bit deeper dive into the TCFlower based approach. So as Johan mentioned in the previous presentation, Open-NFP is a fairly well-known and widely used switching implementation. So it's a virtual switch. It runs in software. But being an offload-oriented kind of company, we push it down into the hardware. It has a match action scheme. It's configured via two interfaces concurrently, one being OpenFlow, which is where the flows are implemented, and the other being OVS DB. And this is for other types of configuration, such as adding and removing ports from the switch and so on. It's accelerated using a flow cache. So typically, the flow cache is the fast path, data path. And when a flow is not present in the cache, it bounces to the higher layer, which usually lives in user space, or which lives in user space, which then programs a flow into the cache. And flows that are not used for a period of time are usually removed from the cache. We have megaflows. This is a type of mask flow. And the reason for this is many reasons, but by using megaflows, for typical use cases, you can reduce the number of flows in the cache, which reduces cache contention, and it also reduces the overhead of managing the cache. Maybe unlike a typical switch, it also allows a variety of other features like tunnel termination and origination. We can also do QoS. Rate limiting, which in OVS world is called metering, but that can mean different things to different people. The list goes on. This is not a presentation about what OVS is, so I'll just leave it at this slide. So the data path, this is a pretty simple representation of how it works. But at the bottom we have the kernel, where the data path lives. There are other implementations of the data path which may not live in the kernel, but the model is more or less the same of the OVS data path is a cache. And when there's a miss, so when it doesn't know what to do, it pushes it up to OVS DB and then OVS vSwitch D, which then makes a decision about what to do, pushes the packet and the flow back down again. And OVS vSwitch D is also managing the cache, so it's actively polling it for statistics, and it uses this to determine the liveness of the flows, and that determines whether or not it's going to evict the flows. It looks kind of straightforward here. Of course, there's lots of details that make it quite difficult. Okay, so now I'm going to look a little bit at two different ways we might offload this. So actually, in a sense, this is offloaded, in the sense that the user space is offloading to the kernel, and the kernel can process the packets much faster than if they would all have to go up to user space. But also, maybe obviously, there's limitations of the speed of this. The kernel can only process packets at a certain rate. It has to do many other things because it's a multitasking operating system. So you may want to get a performance boost somehow by pushing the data path down to the hardware. So talk about two different models for doing this. Now, from a data path point of view, from the packet processing point of view, they're basically the same. The difference is in the control plane. So how you administer the system, or how the kernel interacts with the hardware. So the model that's used in the Netronome Agilio product can be summarized thus. So it's the same as the previous diagram, but I've just added this extra layer at the bottom to represent the hardware. The hardware, of course, is always present, but so it's just extending the cache model. So we imagine a packet going through the data path. If there's a flow present, it's processed straight away, no problem. If it's not present, it's pushed up to the kernel data path. Typically, it wouldn't be present there either, so it will go all the way up to user space. User space then decides what to do with it, pushes the flow to the kernel, which at this, well, not at the same time, but as that's happening, it's pushed down into the hardware. This is fairly straightforward. It's not very invasive, and it works. It's kind of nice. It doesn't offer you a lot of control over what's happening, because there's no direct control path between the vSwitch D and the SmartNIC. Everything goes through here. So for Metronome hardware, which can generally offload pretty much everything and has a very large number of flows it can store, this works out okay. But if you were in an environment where you had, where the hardware had some kind of restrictions, like maybe there were a large number of flows it didn't want to offload, or there was a limited number of flows it could offload, you may want to be able to manage this more actively. And that's not really easily done in this model. So we move to the next model, which is a little bit more complicated. So we can see now we've gone from 1 all the way to 3 different data paths. So how does this work? There's lots of arrows. It's maybe not obvious how they all connect up to each other. So firstly, we have the SmartNIC. This is where the packets enter the system. If there's a flow, if there's a hit there, the flow is present, it just keeps going. That's pretty simple. If there's a miss, it goes up, not to the OVS data path, but to a different subsystem within the Linux kernel called TC. And if the flow is there, of course, it gets processed, but typically it would not be there. And it will go all the way up to OVS vSwitch D. But yeah, this is kind of, sorry, it's a bit complex. But so the miss will go here, then the miss will go here, and if it's here, then the packet gets processed. But if it's not here, it goes all the way up here. So it's obfuscated somewhat at this point. vSwitch D then decides what it wants to do with it according to the OpenFlow flows that are present. It would then typically try to program a flow into the data path. So firstly, it tries to program it over here. And if that works, then this would typically also push it down to the hardware. If this fails for some reason, like a TC doesn't support the flow we're trying to push in, so for example, if you're trying to push an MPLS action, which doesn't exist at this time, then this is not going to work. So then it pushes down this. So in a sense, this becomes your fallback. It's still accelerated in the sense that it's faster than user space, but it doesn't push the flow down into the hardware. So we have 2 different sets of control paths here. We have one that goes between user space and OVS data path, and one between vSwitch D and the TC data path. So in a sense, the TC data path is used for controlling the hardware, and the OVS data path is the existing software mechanism. And this somewhat more complicated model, so we've gone all the way to 3 data paths now. The motivation for this is that it addresses various concerns with the hooks model. In particular, for less fully featured hardware, it's easier to, well, it's not easier, but it allows one to push managing that back to vSwitch D. It could have, or to user space, it could have some intelligence about where to place the flows based on various characteristics of the hardware that it knows about. Okay, so that's the end of the discussion of the models. So TCFlower based offload is an implementation of the second model. And this is interesting to me and hopefully to you, because this is the model that looks likely to be accepted into the upstream, both the kernel itself and OVS upstream. And being an upstream-oriented person, I think that this is very important for various reasons, including long-term maintainability. It's been reviewed by so many people. And having tried very hard for many years to try to get a solution that's merged, it looks like we might be close. So this is also kind of exciting. So I'll just explain a little bit about what TCFlower is, which fits in with the discussion so far. an obvious of what OVS TC is, which follows naturally on. I'll look at an example of how you could modify part of the system and get your hands a little bit dirty. And then I'll throw some little bit of information about where the discussions are going on and where this is going and how you could participate. So TCFlower. In the TC, Linux TC is often associated with QoS. And it does have excellent QoS facilities, but it's not limited to being used only for QoS. So one of the facilities that it has, which is to have things called classifiers. So this is, a packet comes in and it makes some decision about the packet based usually on its contents or its input port or some kind of metadata. There are quite a few different classifiers. One of the newer ones is called Flower. And incidentally, it's called Flower because flow was taken, so we add the ER to the end. So it allows a match on a packet with quite a wide key. So this is quite similar to the way OVS works. And TC also provides actions, which allow you to do things like output a packet to a given port, of course, drop a packet, maybe add some VLANs, modify the packet, and so on. Again, this is fairly similar to OVS actions. So we can combine these two things, this newish TCFlower classifier and the existing TC actions and also newer TC actions to program flows that are similar to OVS, or really you could maybe arguably say that architecturally TC is a superset of OVS, although TC doesn't necessarily have feature by feature. It isn't feature by feature able to do everything that OVS does. So maybe take a little bit different look at the same thing, TC and OVS. So a more table and flow-based look. So in OVS, there's a single table. So often in a hardware pipeline, you have multiple tables and your packet progresses through the system. In OVS, it's just one big flat table, and you match as many or as few fields as you want. There's always a match on the in port. So this is kind of important because it means that because each flow has an exact match on the import, and an import, if you had logical switches, an import would only ever belong to one of them. It means that each flow only belongs to one logical switch. So even though there's a single flat table or a single flat data path, you can divide it up into logical data paths. As I've mentioned already, the flows have a very wide key, so you can match on not arbitrary, but many different fields. And the flows are disjoint, so they don't overlap. This is maybe a little bit implementation detail, but it comes out to be kind of handy. So the flows in the data path, a packet, it's not arranged such that there's priorities and you hit the highest priority packet rule, even though some of the lower priority rule might have also matched. There's always exactly one match. And this leads to it being able to be partitioned, as I already mentioned, based on the import, but there's also other fields that can be used to create sort of separate areas of the table space. And the megaflows are priority independent. Okay, so we compare this to TCFlower, which is somewhat differently architected, but can sort of match up here. It was single table only until a few weeks ago. It now has multi-table, but clearly if you have multi-table, you can do one table. It's actually attached, or when you create a classifier, you actually attach it to the input port. So this is similar to matching on the input port. Again, the flows have a wide key, so this part's similar, although the keys aren't exactly the same, but they're sort of converging as well. And there's only one mask priority, so this kind of matches up with this does actually match up a little bit with the way OVS works internally. Is that typically you will try to match the flows for a given mask, and if that doesn't work, you match the flows for the next mask, and so on and so on. We call it, might be called repeated hashing. And TCFlower, also does the same thing by enforcing that at each priority level within a TC rule set, you can only have one mask. Okay, so, oh dear, there's a return there. Sorry about that. This is a different diagram, different colors, because I made it on a different day. So this is more of a software component view of the world, or a control plane view of the world, rather than the data plane view of the world. So if I have a flow, and I want to add a flow, firstly, OVS vSwitch D, if this feature is enabled, would try to push it down into TCFlower. And then it would try to push it down into the driver, if the driver supports the hook, the offload. And then the driver would try to push it down to the SmartNIC, which could also reject it if it didn't feel like taking it for any reason it chose. If any one of those three stages fails, then OVS vSwitch D will try to push the packet down into the kernel data path. So this is kind of the basics of the system. And as I mentioned earlier, we have three data paths here, although they're not enabled as such here. It's 1, 2, 3. And we can control where the packets go into these data paths. So OVS vSwitch D can choose to put it into the kernel OVS data path or over into TC world. But within TC, we can choose whether or not to put it into the software implementation or the hardware implementation, or both, using some flags. And typically, you would choose to only put it in to the hardware, which is termed as skip software, because there's not really any reason to have it in the software. But it depends what you want to do with the system. And I mention this particularly because actually it will come up again in my follow-up presentation. Okay, so how does this relate to what Metronome is doing and why I'm standing here? So we are implementing this for the NFP. We've been involved in various parts of the diagrams I've popped up so far. The user space part, we're working on helping to get those patches merged. The kernel core part, we've contributed various patches and been active in reviewing others. And we're also actively working on implementing this solution for our upstream driver and of course, the accompanying firmware. So what is my roadmap work, if you're interested? Or what is it that I'm busily working on these days? Well, not just me, but me and my team. So stage 1, we're going for something pretty simple here. It's L2, L3, L4 matches, not all of them, but the most interesting ones, L2 and L3 addresses, IPv6 labels, L4 ports. On the action side, things are a bit more limited, somewhat more limited than OVS. We can drop packets, we can output them only to one port, and we can do VLANs. So this stage 1 feature set is modeled on, well, not modeled, it mirrors, with the exception of VXLAN, what is being pushed into OVS. So we can't really go beyond that feature set. So that's why that list is how it is. Stage 2, we're at the VXLAN support. It's come just a little bit later because there's a few tricks to be done there. And then stage 3, we get to a bit more interesting part where we actually try to extend what's being proposed and hopefully by then merged into OVS. And so the first cab off the rank there will be the set action. So basically be able to set all the fields that we can already match on. And then beyond that, to basically move towards all the stateless match action support that OVS has to try to be able to do that in TC and in turn offload. All right. So what's the status of this? From upstream point of view, there's broadly speaking 3 different categories of activities. One is OVS TC, which goes into user space. So the patches are available. should be a new set of patches coming out about now, and trying to get this into the 2.8 release. So we have, I think, about a month left running on the clock to achieve that goal. On the kernel, the TCFlower part of it is evolving, but it's also present with respect to what OVS TC is trying to do. So actually the middle part is the one that's ahead at this point, which is nice because it's the one that typically requires the most lead time. And then we have the NFP, the driver work and firmware work, and we're prototyping this. I plan to post this very soon now. The first we did actually. There's already patches going out. There's quite a number of different changes required to achieve this, but the next batch should be coming quite soon. Okay, so maybe this will be the most interesting part of the talk, or hopefully. So I'm going to look at how you might modify TCFlower. There's lots of different parts of this system, so I can't really cover how to modify all of them. But here I've just gone right into the core of the system, how to modify the Flower classifier. And we'll look at 3 patches that achieve adding one small feature. Okay. So the first maybe I should make that a bit bigger. Is that a bit better? So the aim of this work was to add support for matching on ICMP, the type and the code. And so the first of the 3 patches to achieve this was to modify the flow dissector. So this is a part of the core part, a part of the Linux stack, the core stack, which what dissection means is to basically rip apart the packet, to look at all the fields and to put them into a flow structure. What might usually be called classification, but this thing is called the dissector. So it's used by a couple of different things within the Linux kernel. Its main use is actually generating hashes for things like RSS, where ICMP would not be applicable, but it's also used by the Flower classifier. So I made a little helper function just to get a 16-bit value of a packet in a safe way. And then in the main function of the dissector, I said that if the caller has asked for ICMP dissection, then firstly get the part of the flow key where these values should be stored, and secondly use the helper, which was just above, to retrieve those values and store them. So this was it's not a large change. So we'll move to the next change. So this is a companion. So this is the caller of the code you just said. So this is the Flower classifier itself, adding the same feature. And here you can see an example in the changelog of how you would use this if using the TC command line tool. So you can exercise this without the OVS system. And actually this is I should have mentioned this earlier, but another key benefit of this this architecture is that it's not tied to OVS. You can use it outside of the context of OVS. So here I add we see that some new attributes have been added. So this is so user space and the kernel could communicate with each other about the new matches. So it seems like there's a lot of attributes, but it's sort of a 3-dimensional matrix. So we have ICMP for the type and the code, and then we have also the same for ICMP v6, and then each has a mask. And these are just split up into separate attributes by convention. So here the kernel, the code is reading a netlink message, which is coming from user space, and it's just pulling out the attributes which were added just above, and setting them in the flow key accordingly. Yeah, this hunk that's at the top is maybe the most tricky one, or at least the one that took me the longest to work out. We have to tell, we have to set up the dissector such that it will actually perform the ICMP dissection. This was checked against in the previous patch. And then the second larger hunk there, this is the opposite. This is when the kernel is forming a netlink message to push down to user space if user space requests a flow. So it's setting up the new attributes so that the user space can see them. And then that's the end of that patch. And the last patch, which is not strictly necessary from a kernel or an OVS point of view, but is very, very useful for exercising it, is to modify the command line tool called TC to allow you to add and remove and view these flows. So there's some help text. Some rearrangement of the code. And then we see we can parse the command line. This is a helper function, which will help during the command line parsing. So we're just teaching it about these new IP protocols, the two different ICMP protocols for IPv4 and IPv6. You can see it already knew about things like TCP and UDP. And so this is just another helper function for allowing us to work out which is the right attribute to use based on which IP protocol we're using. So this is just a parsing value, parsing helper, which is going to be used when reading the command line. So we get the value, ICMP type encoding 8-bit values in base 10, just using the existing infrastructure that's present in this in the tool. And then this is more of the command line parsing. You can see most of the work here is just command line manipulation. So we use these helpers we made so far if the user has asked for a type or code for ICMP. And well, it's been all about parsing till now, so obviously we have to go the other way, which is to pretty print the data out we read from the kernel. We teach it about the new IP protocols, and we make a little helper to help it print out ICMP, and we call these helpers if the attributes are present in the message. And that's it. So you see that actually in this patch, in the previous patch, most of the work is in terms of parsing or forming either netlink messages for kernel to user space communication or the command line of arguments of the program. And the actual core changes is really limited to the first patch, which was quite small. So it turns out that ICMP was actually a particularly easy case, which is why I chose to present it here, because we could already parse IPv4 and IPv6. ICMP is just, in this case, it's just a simple matter of reading 16 bytes, 16 bits off the very front or of the L4 header. There are, of course, more complicated protocols where you would have to write more. It wouldn't be so simple as just getting a 16-bit value. So I'm almost finished now. I just go back to my slides. So this is an open source activity. So most of the activity discussion is going on various mailing lists, which are listed at the bottom. And the kernel discussion takes place on the NetDev mailing list. And Open-NFP has a dev mailing list. And obviously there's overlap between these when we're talking about this topic. So the feature set and so on, I mean, this is really being decided by the people who are working on the code, but it would be really good if we got more input from people who are using it. So for instance, which fields are good to add to the match earlier than later and so on. Otherwise, we kind of just make a best guess. And thank you very much for your time, and hopefully we can have some coffee soon.